Okay, and can start with the second lecture of Jialun, and title is Projection and Non-Concentration on Arithmetic Sequences, and you already have the blackboard.
Thanks. This is the third lecture of this mini course, and today I will not talk about the computational entropy, but move to other things, other materials that we needed in the proof. So let me recall the theorem, the main theorem about the dimension of the station mirror. So first, we will take a new, it will be a finitely supported probability mirror on SO3R, such that the group generated by the supporter nu is a Zariski dense subgroup in SO3R. And moreover, this subgroup satisfies a so-called exponential separation condition. So for example, if the group generated is discrete, then it's exponential separate, satisfy exponential separation. And also yesterday I gave a definition of the exponential separation in the question session. So if you want, I can recall the exponential separation. Otherwise, I will go on. Yes? Yes. So exponential separation, it means that there is some C positive such that for any n large, then for any xy inside the support or mu convolution n times different. For different points in the support, we have the distance between xy is greater than exponential minus cn. So this kind of condition. Here the distance, we can just take some Riemannian distance in SO3R. Just fix one. Yes? The C should be very large. Very large, yeah, very large. Because it's a weak condition indeed. It can be very large, but you need to have this kind of scale. That's like what I mentioned yesterday in the last part of the lecture here, computing the entropy with respect to the partition. Because in the partition, at level n, the size is like exponential minus n. But you can make the partition much thinner, but still you are in exponential size. And that's the place that you can get the random walk entropy. So something like this. Then once you have this, but one more word. But indeed, even though this kind of condition seems not strong, but it's very hard to verify. The only known example, I think we know for discrete groups, also the group generated by algebraic, if the entries of the group, entries of elements, they are algebraic, then we can verify this kind of condition. Otherwise, I think very few is known. So it's an interesting condition, but somehow it's very hard to verify. Yes. Then if the support to nu satisfies these two conditions, then the unique new stationary mirror mu, it has this kind of dimension formula. The Hausdorff dimension of mu can be computed by something simpler called the Lyapunov dimension of mu. So let me also recall the Lyapunov dimension. This one, the Lyapunov dimension of mu is equal to, there are two parts. Either you are is the first Berg entropy divided by the difference of the Lyapunov, lambda 1, lambda 2. Or it is 1 plus the first Berg entropy minus the first part. Lambda 1 minus lambda 3, yes. And this case is where this case you have this first Berg entropy is smaller than the difference of the first two Lyapunov. Otherwise, and here, as Wenyu mentioned, this is some kind of entropy which will be complicated. So she will talk more about this first Berg entropy tomorrow. And lambda 1, lambda 2, and lambda 3, they are like the three Lyapunov exponents. Lyapunov. components of the random walk. Yes. So the first part of the talk, I will try to explain how can we get this dimension formula from another dimension formula for the projection. So first, I will define the projection. So let's take V inside PR3. So here I see V as a one-dimensional subspace in R3. You can also see as an element in PR3. So then we can draw a picture like this. So V will give some point in this the space of the ball is representing PR3. Then then this large circle is we call it the V perp, is the subspace which is perpendicular to V. And then we can define the projection, the pi V perp. This map is, so for any point here, if you take some point x here, then the image, then we can draw a large circle passing through x and V, a large circle. Then the large circle will intersect this V perp, this large circle. The image is called the V perp. This one is called pi V perp x. So pi V perp x is the intersection of the V perp with the space generated by x and V. Yes. So this is we call it orthogonal projection. Indeed, it's a spherical projection. Yeah, once we have this, then we can state another, the results for the projection. It's the second main theorem. So under the same condition, so yes. Before state theorem, I still need to introduce another thing. It's called the new is. We introduce new minors. It's like the inverse of the original random walk. New inverse G is defined as the new G inverse. So just in a support of nu, you take every element to the inverse. And then we can have this mu minus is the new minor stationary mirror. Then the theorem of the projection states like this, under the same condition of the previous one. For mu minus almost everywhere the V. So here, this is still a stationary mirror on PR3. Now you different random walk. Almost this way, you have the dimension of Hausdorff dimension of the pi V perp mu. Here is mu. Here is mu minus. So it's this dimension is equal to the minimum 1 and the random walk entropy of nu divided by the difference of Lyapunov of lambda. Yeah, so this is the version of the projection for almost every direction given by mu minus. The orthogonal projection of mu has a Hausdorff dimension given by this formula. The minimum 1 and the random walk entropy divided by the difference of the Lyapunov. Here, recall the random walk entropy is defined by this way. It's the limit as n go to infinity. 1 over n, the Shannon entropy of new convolution n times. It's this way, yes. So now, what's the connection between this theorem and this main theorem? So that's, in order to go from the version of the projection to the original version, we need a tool called which François Le Dapier explained 2 years ago in the same conference. So it's the Le Dapier-Young formula for this case. So let me recall the statements. the Le Drapier-Yang formula in this case. Nice mu. And in this case, it's due to Le Drapier-Lisa and Rappaport. The statement is like, so we will assume the same condition, but indeed, here I will explain later, but let me give a statement. The first one is that there are these two numbers, gamma 1, gamma 2, positive numbers, and such that the first Mach entropy of mu nu is equal to gamma 1 times lambda 1 minus lambda 2 plus gamma 2 lambda 1 minus lambda 3. And the second thing is that the Hausdorff dimension of mu is the sum of gamma 1 plus gamma 2. And moreover, these gamma 1 and gamma 2, they have meanings. They are the dimension. Gamma 1 is just the, for mu minus almost v, this dimension of pi v perp mu is equal to gamma 1. This is the, such that 1, 2, 3, this is gamma 1, and there are also 4. The gamma 2, here gamma 1 is like the dimension of the projection, and the gamma 2 will be the dimension of the fiber. So the statement is for pi v perp mu, almost every x. The fiber measure, let me state xv is equal to gamma 2. So here, so the fiber measure is the fiber measure for this projection.
By the way,
yes.
3 is
Mu minus. Mu. Thank you. It's mu minus. Yeah. So the 3 is fine. It's just you have a mirror on this space after projection. It's a mirror on one-dimensional space. It's the dimension of this one. And the 4, so for each projection, then you can define the fiber measure. The fiber measure is defined like this. Just to briefly recall, the fiber measure is something, unique family of probability, almost surely a unique family of probability measure, such that if you integrate this one with d pi v perp mu x, you will go back to this mu x. And each one, and also this mu xv, they are measures on the fiber. On the fiber. The fiber is given by x and v. It's a large circle.
Or is still mu minus almost every v?
Yes, the same. Yeah, you also need this one. Yeah. Mu minus almost every way, and v and yeah. Thank you. Yeah. Thank you. It's mu. Yeah. It's mu. Yeah. So that's a statement. Then using this theorem, using this Le Drapier-Yang formula, we can go from the projection version to the original version. So let me give the proof. The proof not difficult. Not that difficult. Proof. Yeah. Yeah, before going to proof, I need to mention a bit that, in fact, this theorem works much more general. It works for higher dimension. And the assumption is also weaker. We don't need the exponential separation. But we need some kind of moment support. Still need to find countable support, something. Yeah. So it's a general theorem, but we can use in this case. the proof. Now I'll give the proof. How assume this theorem? Assume the theorem of a projection. So proof is from dimension of projection. Projection to this dimension formula, to this one, to the Lyapunov dimension. So there are two cases. The first case is when the house. The first case is when the random walk entropy is small. When this one is less than 1, then we have then the first equation, it tells us that this gamma 1 first equation tells us this gamma 1 is no, there are two things here. So first, from the theorem there, we can get this random, since this is less than 1, so in the minimum, we will take this one. Lambda 1 minus lambda 2 is exactly equal to the dimension of the projection. So which is exactly gamma 1 by the Lyapunov formula. And for this one, and then from the first equation, we know this one is less than the first back entropy divided by lambda 1 minus lambda 2. And then now, you have so from this you get random walk entropy less than the first back entropy. But there is a general fact that this kind of first back entropy is always less than the random walk entropy. Here is some general fact. General fact in this case is due to Kamenovich. So the first entropy always bounded by random walk entropy. So by this, yeah, exactly. It's like it's like you have because nu is a random walk. So if you have an action of nu on some variable space x mu prime. So if you have some action of nu on some variable space x, and this mu prime is some station mirror under this action of the mu, and this is called some boundary of the action of nu, and there is some concept of the boson boundary, and the boson boundary is like the most general case, which this kind of thing will always be a factor of the boson boundary. And in the boson boundary, the random walk, the first Mach entropy will be exactly the random walk entropy. And for factors, their first Mach entropy will be smaller. So there's some theory behind it. So from this one, we conclude that the random walk entropy is indeed equal to the first Mach entropy in this case, and which also implies this formula stuff. No. Yeah, they are equal, and this and they are equal, and this gamma 1 should be also equal to this one. So then gamma 2 must be 0. You have no choice here. You imply this stuff. And the case 2, case 2 is simpler. Case 2 then, case 2 is exactly means that this dimension of the projection, gamma 1, dimension of the projection is equal to 1. Since the case 2 means that this random walk entropy divided by lambda 1 minus lambda 2 is greater than 1. Then from the theorem of the dimension, you know this dimension must be 1. It must be 4 dimension. So it's 1. Then you have no choice. then from 1 and 2, you get the result. Things like this stuff. So that's the proof how we go from the theorem of the dimensional projection to the dimension, to this dimension formula star. And the idea is always like you have this, the first equation tell you a restraint on the linear combination on gamma 1 and gamma 2. But the ideal Lyapunov dimension is like you need to make gamma 1 the biggest possible under this constraint. That's the idea behind this proof. So that's the first part. How do we get the dimension formula from its projection, from the dimension formula of the projection? Now the second part of talk, I will talk about another ingredient we need. So first, recall the entropy growth argument that I stated yesterday of Hockman, but today I state a much more precise version. I give all the quantifiers, and so you see it's a bit complicated. And yesterday I talked about the condition, the second condition of positive entropy, which comes from something like contradiction hypothesis and the random walk entropy. And now today, but I didn't explain the third condition, which is called something called entropy porous. But today I will also not give the definition of entropy porous because it's something complicated. And but I will talk about something which, some technical tool that we need to prove this kind of entropy porous. This is called the non-concentration or arithmetic sequence. Let me state it, and you will see how it comes from. Why we need this kind of thing. Yes. Some arithmetic. I will abbreviate this NCAS. And the statement is like this. Definition. So mu is a probability measure on the unit circle R over Z. Not unit, on R over Z. And Z. Mu satisfy. And CAS if for any delta positive, there exists K0 and some L integers greater than 1, such that for any K greater than K0, we have a measure estimate. So the measure of the union of n of the ball centered at n over 2 power k or radius 2 power k plus L is less than third. Yes. Here n is chosen from 0 to 2 power k. You will need this kind of property. So it's the measure of mu near this kind of point, near n over 2 power k, and the radius is 2 power k plus L. It's like you have interval and you do some you look at some point, then we need some estimate or neighborhood of this kind of thing. And this somehow this condition comes from the definition of partition, because yesterday, in order to compute the entropy, we need to compute entropy with respect to the two-edged partition. And in the definition of the two-edged partition, we will choose a starting point 0, 1, You choose starting point 0 and look at all the two-adic partitions starting from 0. But in reality, when you want to prove the entropy porous, so to compute some entropy, sometimes you need to shift a bit the partition. The partition not always starting from 0, maybe slightly different. So in this case, you need somehow some continuity, some property of continuity, and that's where this kind of condition comes from. We need this kind of condition to ensure there are sufficient continuity when you shift a bit the partition. So it comes from the partition, some continuity of the partition. Which comes from some continuity. Or shifting of partition. Yeah, and this NCAS property looks not that difficult to verify. Indeed, it's not that difficult. So in some special cases, it's fine. So first, it's a lemma, like it's a simple property. Like if mu satisfies decaying property, then this NC satisfies decaying property. Which means that there exists epsilon less than 1 and some c greater than 1, such that for any small radius R0 and x inside x in the R over Z, we have the decaying B x R over C is less than epsilon mu x R. Less than 1, less than 1. Yes, thank you. Yes, it's decaying. So if there's some uniformity decaying, so once you replace the ball BXR, once here is the mirror of the ball, radius R. If you shrinking the ball to the radius R over C, then the mirror is decaying. Mirror is smaller, and there are some uniform constant epsilon here. So that's called the decaying property of the mirror. Once you have this property, then you can prove that NCES. Just try to iterate this inequality to make epsilon sufficiently small. Then you can get that one. But the difficulty here is that this decaying property is a bit hard to prove in this case. No, we don't know how to prove this property in this case. Then, yeah, I didn't, yeah, then NCES. Yeah, that's a complete statement. Yeah, now let me state the difficulty. The difficulty here is that, like in the previous work of the Baroni-Hochman-Rappaport, which mentioned by Wenyu, in their case, they are considering the uniform contracting self-affine fractals. So you have uniform contracting. But now, we are in this PR3 case. The action is average contracting, but not uniform contracting. So it's not uniform contracting. So I don't know how to prove this NCES. Don't know how to prove uniform, how to prove the decaying property. Decaying property for our family of mirror, it will be this kind of projection pen. We need to prove the decaying property of the projection mirror, but we don't know how to do it, so we choose another way. So that's where comes the Fourier decay. So let me do a quick definition. Yeah, definition. Again, mu is a probability measure on the circle R over Z. Then I say mu is Riemann measure. Measure if the Fourier coefficient of this mu go to 0. Go to 0 as k go to infinity. Here, the Fourier transform is defined by just the classical one, 2 pi I xk mu x. And then I will try to give a proof of the proposition that is this Riemann measure property also implies NCAS. It's a replacement of the decaying property in this case. It's a proposition that mu Riemann implies mu NCAS. Yes. Yeah, so that's then in the remaining time I try to give the proof of this proposition, and I also try to state the version of the Fourier decay that we used, because we need to treat this projection case, so it's a bit more complicated than just the circle case. Yeah. Yeah, it's related to the proof of the porosity. Yeah, we use this NCAS condition to prove the porosity. Yes. Yes, in any way, if you know some other way to prove this decaying property or this projection, to let me know. Yeah. Yeah.
Your measure mu has a first.
Yeah, but Firstman property is not enough.
Is that not enough?
No, it's if you just use it trivially, then it's not enough because you have a lot of interval. Like the number interval is 2 power k, so the size is it's something more delicate. But maybe there are some more clever way to use Firstman property or some dimension to prove this. But since in this case the Riemann property is available, so we just use it. But there, of course, there may be other ways to prove this NCAS condition. Here. No. No, exponential separation is like yesterday. It's really used in the last step. You need to, it's in the step when you want to relate the entropy to the random walk entropy. That's the only place we need the exponential separation condition. Yeah, so let me give the proof. So it's like some exercise of harmonic analysis. So first, we will take a function like this. First, we'll take a bump function. F is a bump function. Bump function. It's like this. You have the circle and you have a 0. Then you look at the interval of size 2 power minus L. And here minus 2 power minus L. And you want this function to be equal to 1 in this small interval, in this smaller interval, identically to 1, and then decaying to 0 outside it. It's like 2 power minus L minus 1. So more precisely, what we want is that the F restricted to 2 power minus L, 2 minus. This is 1. And the support of F is not too large inside. And F is some like smooth function, say infinity. Yes. First, we take a function like this. Then then I define another function, large f, x is equal to f 2 power kx. Then the first property, the first thing we need to observe is that then fx restrict to this union equal to 1. The union of the n, the ball, be n over 2 power k, 1 over 2 k plus l, is equal to 1. Yes. This one equal to 1. Yeah, that's because if you take some point x inside this interval, then you take you multiply by 2 power k, then it will lie in this interval, because you are in the R modulo z case. 2 power k. I just choose this function by purpose. And yesterday, when I verified the computation, I found some small mistake in the paper. So it's good to prepare mini course. Yes. Yeah. First, you have this property. It's just by definition. Then we try to compare the error. So it's then mu on this set. So I write again. 2 power k. It's the last time. Then the measure will be smaller than the integral f d mu. Then we can do the Fourier analysis. So then this sum is this integral is equal to, if you sum over the frequency, but the frequency in z, and you look at the transform Fourier coefficient of k at frequency minus c, and the Fourier transform mu at frequency minus c. Yes. Then we need to compute this term. What's this term? Let's do the computation. It's just the integral of fx e 2 pi I cos cx and dx. And then you can use the definition. It's f small f 2kx exponential 2 pi I cos cx dx. And then observe that if we will now I will try to do the changeable variable fy. I will replace 2 power k by y, but then the pre-image of y, they have 2k options, so they are not unique. So we need to sum over all the 2k options. We also doing this changeable variable, we need to divide here 2 power k, and this will be dy. But here we will have 2 power k terms. So here is the sum over n greater than 0 less than 2 power k. And in the exponential, it's exponential 2 pi I cos c. It is y. No, not enough, please. It will be y divided by 2 power k and plus n. No. It's y plus n, yes. Y plus n divided by 2 power k. Yeah, dy. Due to the special choice of this f, this expanding condition, we get this term. You have the sum over n in here. But then we observe that sum over n, a lot of them will vanish if cos is not divided by 2 power k. Just look at the sum n greater than 0, less than 2 power k, 1 over 2 power k of the exponential 2 pi I cos c n over 2 power k. So this classical thing, it's either 0 or 1. It is 0 if if 2 power k not divide c, and it is 0, it is 1 if 2 power k divide c. So then in the original computation, we can do the change of variable. Again, we can write the only non-zero terms in, there are some, yeah. Now we will go back to that one. Now we will do the change of variable. We'll replace c by 2 power k times g for some g in z. Because all the other frequencies, f hat c is vanishing, is equal to 0. So finally, we will get this. So again, this f d mu is less than. We only sum over g, and the terms will be. Yeah, I still need to write here. Yeah. I will do this one, then once I replace c by 2 power k times g, then in this one, in the computation, this part will vanish, and y, yeah, in other words, it says will be equal fy e 2 pi I g times dy, which is just equal to the Fourier transform of f at g. Yes. So we do the change of variable. Then for the frequency not divisible by 2 power k is 0. If it's divisible, then you'll get this one. So now we can rewrite the original estimate. Then this integral f d mu is less than sum over g, and it's f transform g plus mu at minus 2 power kg. At this stage, then it's some classical thing. Then we will try to estimate this one. Take absolute value. Estimate this one first. This one. No, there's one term. Is the 0 term is important. So f is f0 and the mu hat 0. And for all the non-zero terms, for g not equal to 0, we will do this trick. Take fg. And the supremum is the last one. And times the supremum of g non-zero of the mu hat 2 power kg. Yes. So then the original merit estimate is replaced by this estimate. And for the 0 term, it's simple. F hat 0 is just something less than 2 power minus L minus 1 something. And mu hat 0 is 1. And this is summable because f is some smooth function. It's summable, and you can add some term like f2. You need something like the C2 norm. C2 norm is sufficient to bound this sum. And then the last part is bounded by the Riemann property. So last part, this one is will going to 0 as k go to the infinity. So as k going to infinity, then all these terms, they have very large coefficients. It's 2 power k. Because every element here has at least the absolute value is at least 2 power k. So as k go to infinity, it's like the frequency go to infinity. So from the Riemann property, you know it's going to 0. So this is from the Riemann property. So that's a proof from the Riemann property to this NCES. It's just some classical Fourier analysis. Then Then I try to talk about how we prove the projection measures, the judgment measures. Yeah. Yeah, I don't think it's necessary. Yeah, maybe. Oh, average decay. You are right. The average decay. Possible. Yeah. We can talk later. Yeah. Average decay. Yeah, but nevertheless, I will talk about the Fourier decay. So, how do we prove the Fourier decay in this case? This is the proof. Now it's how to prove. This pi v per mu is judgment. Now we are going to the last part of the talk. How do we prove this projection measures, the arrangement measures? In order to talk about this, I need to introduce another thing called the flag variety, because in order to state the Fourier decay property in the projective space, somehow we need to talk about the flag variety. It's some difference between the conformal and non-conformal case. I try to emphasize it at the end. So the definition is a flag variety. So the flag variety F is a space given by V and W. Just erase this one, yes. Okay. The V and the space of V and W where V is a subspace of W, subspace of R3. And the dimension of V is equal to 1, and the dimension of W is equal to 2. So that's the flag variety. It's like something in the V part. The V part is just the PR3. So we have in general we have the picture like F go to V, PR3. And here we will map some flags VW just to the part V. Then you'll get the projection from the flag variety to the projective space. And then in this case, the flag variety is like some quotient space of the unit tangent bundle of the projective space. So I will try to use another. So for VW, I will also write as for later use, I will also write as X and X plus V. Where this X is XV they are vectors or unit vectors. And X is perpendicular to V. So we will choose some representative in the space, and this is the choice. For the flag, I will also write X and X plus V. Then, after preparation of this language, I can state the Fourier decay in this case. Which is from my thesis. So in this case, it's again we'll have a similar assumption. This mu will be some probability measure on R3 or SO3. And you have some theoretic dense condition. And also you need some exponential moment condition. Now it's not separation, exponential moment. So for example, you just take the finite support is fine. And then that's a condition. Then the statement is that for C large. For some large frequencies here, no. There exists some epsilon 0, epsilon 1 for any alpha. It's a bit technical, but it's like this. For any alpha between 0 and 1, it's a Herd constant. It's Herd continuity, and epsilon 1 is greater than 0, such that for any function phi, which is C1 plus alpha in PR3, and the function R, which is C alpha PR3. Which satisfies some condition like the C1 plus alpha norm is not too large, and the C alpha norm or R is also not too large. It's less than C epsilon 0. And there is another condition where we will use the flag variety. It's the mu f of the x plus v, such that the d phi x at the derivative at the partial derivative x at the direction v, if this norm is less than c minus epsilon 0 is small for some kappa. Here's some kappa positive. Then we have the Fourier decay. It's the statement. Then the integral exponential I could see phi x rx d mu x. This one is less than c minus epsilon 1 plus c minus epsilon 0 times kappa. Oof, it's a long theorem. Yeah, I try to explain later. So mu f is the stationary on this space. So here, in this flag variety, you also have the action of SO3R. You have the same action of XO3R, and and it's a theorem of Furstenberg that in this case, you don't only have the stationary on this space, but also on larger space, this F. And indeed, this one, for the discrete case, it will be over the boson boundary. So you have some stationary mu F here. And here is some stationary mu. And the mirror mu is the projection of the mu F under this projection. So this kind of measure. And the statement, epsilon 1 is something here. Epsilon 1, yeah. Yeah, the thing I want to emphasize in this statement is really this point. This point is somehow something different in this non-conformal case. In the conformal case, so let me try to give some intuition of this one. Why do we always need this one? There are, first I give some intuition, then I give some example. So the intuition is that now it's non-conformal case. And in this kind of story, I'll try to estimate the Fourier decay. We'll fix some point x. When we'll zoom in, it's a very small neighborhood of x, small. Then we go to some small neighborhood of x and look at the support of this mu. And take another point y. Then we try to compute the difference between phi x and phi y. Because that's where the oscillation comes from. We need to look at the difference, and difference should vary. Then you have some oscillation, you can have decay. Then how to compute the difference of them It's because x, y, they are very close. It's a very small ball. We zoom in. So it's more or less the d phi x minus y. But now, here comes the non-conformal property of non-conformality. Because here is the action is non-conformal, so somehow this direction from in a small neighborhood of x, this direction x, y, in some cases they will be very restricted, because in this non-conformal case you'll map in the tangent bound, unit tangent bound, you will map a unit tangent circle to some ellipse, so you have some preferred direction. For most direction here, you have some preferred direction. So in reality, in some cases, if you zoom in very close to x, then the direction x, y, they are not very rich. Most of the directions they will concentrate on some specific direction. It will happen in some cases. So then, this one, since the direction not rich, you will somehow all very close to some specific direction v. So, but then that's bad. So but then if this v is just in the kernel direction of the differential, then that's bad. So that's the way we need to add some assumption like this. And in the conformal case, it's different. Because in the conformal case, if you zoom in, you look at the small vectors from x to y. Since if you assume some irreducible conditions, then the cocycle will tell you that your vectors, they are rotating a lot near x. So you will not have this kind of preferred direction v. So that's this condition really comes from this kind of difference between conformal and non-conformal case. And I can also give some example. Why is it? Do I still have one? No. How much time do I have? 3 minutes. 2. I still try to give an example. So recall what the first day, like the surface group inside SO2R, okay, again embedded inside SO3R. And here it's irreducible. Irreducible, then you can perturb. Rho prime is a perturbation. Rho, which is Zariski dense. Yeah, it's Hitchin, exactly, it's Hitchin. Then the limit set, then the special case, in this case, the limit set of rho prime gamma, it is C1 plus alpha circle. And if we are in this case, then the stationary mu is always supported on this circle, this C1 plus alpha circle. So for here, you can construct some phi, which is C1 plus alpha, such that phi restrict to this circle is exactly equal to 0, and the gradient is non-vanishing. It's always non-zero. Yeah. So in this kind of scenario, you really need to care about the direction v. Because you have this case, it's really 0, but somehow if you just put some gradient or this kind of condition, it cannot, it's not sufficient. So then, so in order to put regional property, we will take this phi x is just equal to this pi v perp x. And then you can verify everything for this function. Because the vanishing direction, d phi x, it's dy v. D phi x v equal to 0 is just the place where x and x plus v. I think it's just the v is inside the original fixed v. From a picture like this. If the tangent vector in this direction, then the image is not changing. So that's a bad direction. And this kind of bad direction is indeed a very special subvariety. We can show the measure is small. So thanks.
Thank you. Any question?
Yes.
The application of this theorem, what will be phi and what will be gamma?
What will be
Phi and what will be gamma?
V and what will be gamma? V is phi. Phi is this one. Which phi? Which one? In this phi. This phi. This phi.
Oh, it'll be the projection.
Yeah, phi is just a projection. Yeah. And the gamma in the application, like for the anosov representations, it's just nu is probability measure supported on the group rho gamma. It's some discrete group. And when you will mention it tomorrow, I think she will explain the exact setting we need.
More questions before tomorrow? Okay. Thank you again.
Thank you.